Hello students, over the past three lectures we have been looking at the data path and control path to um, execute the instructions, right? So we took one instruction at a time and we were looking at all the um, control logic or control signals and how they would be triggering each of the other logic modules and eventually execute that instruction. And when we say execute an instruction, for the load instruction it would reflect as a change in the destination register, and for ALU instructions, um, basically the arithmetic and logic instructions, it would reflect as a change in the register value again. And if it is a store instruction, then the change would reflect in the memory location where we were trying to store the data. And if it is a control instruction, the change would reflect as a change in the control flow. So the data path that we built, right, is helping us to achieve this. And a quick uh, recap: we divided the instruction execution entire thing into five phases or steps or stages, you can say. The uh, fetch step, decode step, execute step, memory access step, and write back step. Now, I did not touch upon the time aspect of it, and that's what I'm going to discuss in this lecture. It will be a very short lecture, but very much focused on um, the timing issues, right? So yes, we have built the control path and data path. Now, if you want to understand how much time does it actually take for us to execute an instruction, how would we determine it is basically the data path of that instruction would help us decide, right? So for example, for any instruction, the fetch stage would take some time, meaning that the PC will be sent to the memory will respond with with data that we place in the IR. After that, we have the decode step, wherein we look at the IR and figure out which instruction it is, and at this eventually we'll identify the register operands and the immediate field if it is required, right? And in the very same step, we are also contacting the register file and getting the values of these register operands. In the third step, which is the execute step, we are taking these values from the register file and processing them in the sense performing the operation. It can be add, subtract, multiply, divide, shifting, etc. Right? Now the execute step can take different time for different instructions. Right? Typically, the multiplication operation would be slower when compared to an addition. Right? And so that can have a say on how much time some particular instruction would actually take. Now, beyond that, for a load instruction, again, we take the effective address. In the fourth step, we go to the memory and get some value. And in the fifth step, we write it to the register. So we are accessing the register file twice, and we are accessing the memory twice, and we are performing the ALU operation as required in the execute stage. So all these small blocks would help us to make an estimate how much time an instruction would actually take, right? Now, we also saw that not all instructions would require all these steps. For example, the store instruction will not require the write back step because we don't update any register at the end, right? And the same can be applied for the um BEQ instruction also, right? Sorry, branch instructions, BEQ, a specific example where we will know the output of the branch by end of the execute stage, and probably let's say we'll take one more step uh, to determine the next PC. Even in that case, we don't need the fifth step. Now, if for the ALU, we don't require the fourth step where we are not accessing any memory, right? So effectively, it would need four steps only. Now, can with this point in mind, if you want to build a hardware that would take different number of steps for each, no, based on the instruction, then probably we'll get some better execution time. For example, let's say there were more ALU instructions than load instructions, and we are saying that the ALU instructions uh, would take four steps only. So effectively, uh, we let's say there are like 10 instructions and 8 of them are ALU. So we'll need effectively 32 steps to execute all the ALU instructions, and let's say the remaining two are load instructions. So we need 10 steps for that. So overall it would be 42 steps. But if we want to consider that all the instructions uniformly take 5 steps, then uh, it would effectively take 50 steps. So we can argue that yes, if you want to uh, determine the number of steps based on the instruction and we don't generalize it, so there is some impact on the execution time, maybe on the positive side. But how does impact the control unit, right? The control circuit which needs to generate all the control signals, right? Earlier in the previous lecture I made a point, almost at the end of it, saying that how a possible control circuit would look like. It typically, in a hardware control, we would go for a step counter based thing, right? Now the step counter itself will be the number of steps of this counter would vary on the instruction. Now we need to add some additional hardware there, right? It can disturb the existing uh, modules. Now let's say we have a 4-step counter and a 5-step counter, and based on the instruction we are triggering one of them, right? And so we need a lot of additional logic there. We need to see whether all this effort to realize a complex control circuit will actually lead us to a better execution time, right? Now keep this point in mind. I'm going to touch on this almost at the end of this module again, when we are talking about we'll come back to the performance aspect, right? I'm going to summarize it at the end of module 2. In case I miss, feel free to point it to me. So in general, for almost all the general purpose process that we have, we don't tailor make the data path for each instruction. Okay, the data path and the control path are pretty much standard, and different instructions will go through different go through the same data path but with their own data basically. But if you look at the time, they will be taking more or less the same time, because all of them will be going through the same number of steps. Now the immediate question would be why. That's the reason I said I'll come back to this question at the end of this module. Okay, keep this in your mind. Now assuming that we are going ahead with the 5 steps of execution for each instruction, there can be two possible implementation. One is what's called as a single cycle design, the other one is a multi-cycle design, right? And what do we mean by this? Let's try to understand that. Let's say, and to execute an instruction we need so much time, right? The length of the box can be uh, interpreted as the time. So in the single cycle design, sorry, So in both the single cycle and multi-cycle design, the instruction will go to the fetch stage, decode stage, execute stage, memory access stage, and the write back stage. In the single cycle design, all these stages or steps will together be counted as one cycle, right? The delay of each of these steps will be added, and that would make up our cycle time. But in multi-cycle design, what it as the name says, each instruction will take multiple cycles. Basically, each of these steps would take one cycle each. So the fetch stage would take the first cycle, decode would be the take second, execute third, memory the fourth cycle, and write back the fifth cycle. So if you look at the time it would take for one cycle, let's say here it's x, it would be x here also, in the sense that each of them will be uh, taking each of them will be taking a cycle time of y, where y would be equal to x upon 5. So overall, even in multi-cycle design, if you look at the number of seconds or nanoseconds, they will be more or less same when compared to the single cycle design. Now here there is a very big assumption that we are making, which is that all these five steps, the fetch, decode, execute, memory access, and write back, are taking equal amount of time. We call them equal tasks in terms of time, right? But we all know that it's not the realistic case. Like just like I mentioned in the previous class, sorry, in the previous slide, the execute stage can take more time or less time based on the operation that we want to perform. In that case, how can we match its cycle time, right? And the in the fetch stage and memory stage, we are trying to access the memory, which we know that it's slower than the circuitry, right? So how can we figure out this cycle time? How can we claim that the cycle time will be uniform across all the steps? So that is a very big assumption. I'm going to touch upon this assumption after a few lectures. Okay, again on why this is how we have handled this, right? How we have overcome this assumption, basically. Now, for the moment, just assume that both the single cycle design and multi-cycle design will take the same amount of time, which is x seconds, or let's say x nanoseconds for one instruction, and all the instructions will go through the five steps. Now, let's look at the performance equation, which is the instruction count times cycles per instructions time cycle time. So in case of single cycle design, the CPI would be 1, because all that one instruction takes is one cycle, and the cycle time itself is x. In the multi-cycle design, the cycles per instruction is 5, because each of them will take um, 5 cycles with cycle time of y. And in both the implementations, because we are following the same ISA, let's say we are using the same compiler as well to avoid any other secondary effects, the instruction count would still be same. So uh, in that case, the execution time of the program will be same whether we go for the single cycle design or multi-cycle design. Now the single cycle design can be imagined as if it has low frequency. It means that let's say the frequency of the single cycle design is something like 100 megahertz. But when we move on to the multi-cycle design, the frequency would be, because the number of steps are 5, it would be 500 megahertz, right? Because the cycle time is x by 5. Now the same hardware, which is considering one cycle for each step, will be ticking at higher frequency, but to run the program it would take the same time more or less when compared to the single cycle design. So just by looking at the single cycle and multi-cycle names, we cannot say that multi-cycle design is faster or slower or anything like that. Okay, keep this in mind whenever you are trying to analyze the uh, single cycle and multi-cycle design perspectives. Okay, so I'm giving some example problems for you to work out in the next slide. I'll leave you at this point on or with a question: can we do any better with the instruction execution? Yes, we have built a data path, we have understood how the control signals are generated, and we looked at two possible design options. One is single cycle, other is multi cycle, but we also had some understanding that both of them will take more or less same time. But if you want to improve the execution time of a program, what can we do better at the hardware? That is the second half of this module. And there are it's it's quite open on what it would be, right? I have already mentioned as one of the great ideas in computer architecture, right? It is pipelining. And the whole discussion that we had over the past three lectures is converging onto a pipeline design. Here, uh, the design we are looking at, whether it is single cycle or multi-cycle, is executing only one instruction at a time, right? At any given moment, only one instruction is under execution. Now, in pipeline design, we will be doing much better than that. Okay. We accordingly we need to introduce some changes at the hardware, and they will have secondary effects. We'll understand what they are and what other tricky situations which are called as hazards that we are going to see in a pipeline implementation. It's a very fascinating topic and very fundamental to the processor design. The concept of pipelining was introduced somewhere in 1960s itself, but it's still relevant. And in almost all the processes that you see, right from your embedded cores, like even the small processor that is sitting in your washing machine or ATM or anything from there to the high-end servers, right? Or the processes that are deployed in the data centers, all of them employ this pipelining. Okay, so let's see how we can improve the performance and how much we can improve the performance with pipelining. With that, this is the last slide. Like I said, here are the questions 4.3, 4.5, and 4.8 from chapter 4 of the computer organization and design rescue edition textbook that we are following. Give it a try, you will understand the design implications of the single cycle and multi-cycle design. With that, I will pause this lecture. Thank you.